Break time now. We take a small mental break. Let me talk of some scientists today. It is a hypothetical case. The world is now finished. It is the time after the final day of judgment. The scientists have all done great work for humanity. Based on their scientific work, life has become so easy and so forth and so on. So because of their great service to mankind, they are all in heavens, in the paradise, right? So whether you agree or not. So they are there and they are in a beautiful park and they are talking to each other and so on. And because they are scientists, so they are together by God's wish, that you see these guys together will be much better than mixing them with the other people. So these scientists are saying that, you see, during our life we were always working. Let us now relax and play and so on, and let us do things which are very childish in nature and enjoy them. It's okay, everybody agreed. There is a famous game, you know, in children called hide and seek. This is in English, in every language, that there are some children, they go and hide in different places and one person has to find them. And once he finds anyone, then the game is over, then it restarts. So it is called hide and seek. Seek means find. So they say, let us do hide and seek. So okay. And by toss, the first time, Einstein is the one who has to find the other people. So okay, everybody goes. Einstein has his eyes closed and he is counting 1, 2, 3, 4 and so on. All the others, they go behind a tree, behind a bush, in some hole, somewhere they are hiding. Newton walks 4, 5, 6, 7, 8 paces, then takes a piece of chalk or a stone or something, makes a square box on the ground, makes a mark on a square box and stands in front. Now Einstein says 1, 2, 3, 4, 5. Once he reaches 50, he says, now I have counted till 50, I will open my eyes. He opens the eyes, everybody else is hidden, but Newton is right in front of him. So he starts shouting, oh, Newton is out, Newton is out. Everybody comes out from the hiding. But Newton says, no, Newton is not out. You are wrong. He said, what do you mean? We have seen you. He said, no, Pascal is out. He said, what do you mean? Newton is out. He said, no, Pascal is out. See, this square is 1 meter by 1 meter. This is 1 square meter. And Newton is standing on it. Newton per meter square. Einstein is out. The other type of microscope, which is even more costly, is a transmission electron microscope. Transmission electron microscope. Now you see the word transmission. So the sample is now so thin, the sample is so thin that the beam can go through it. It can transmit through it. You see, normally the beam goes to the material and reflects back. Even in the scanning electron microscope, the electron gun beam goes to the sample and then reflects from it. So the scattered electrons are collected. But this time the sample will be so thin, like a wafer, so thin that the gun will send electrons and so on, which will pass through it, right? And then they will be collected and so on. So they will completely go through the fractured material or the other material, and then we will collect it. So this will be, and there will be bright field image and dark field image, and you can quickly read through it. What I want to tell you, that preparation of this sample is much more costly than the SEM sample. So the sample preparation will first of all be special machines and so on, and the sample preparation will be a very costly sample. So you see, we do only normal optical or digital microscopy if we require it. If we want SEM, then the machine is, oh, I did not tell you the cost. I told you that a normal microscope is about 3-4,000 reals. A digital optical microscope is 40 to 50,000 reals. The microscope SEM, scanning electron microscope, that we bought from the research funding of my group, that is more than 500,000 Omani reals. More than 500,000 Omani reals. There are many other SEMs which are about 1 million Omani reals or more. And this transmission electron microscope is much more than that. So maybe 1.5 million reals, maybe 2 million reals. So this is unbelievable. We do not have a transmission electron microscope in the College of Engineering, but we have it in the College of Medicine, because they want to see very, very fine images of human bones and tissues and so on. So they have it, and we can use that if we like. So the machine is very costly. The sample preparation is very costly. So unless we are sure that we want to do some research where we want to use TEM, we don't do it. And this is the actual picture of a TEM. Again, the size is roughly the same as an SEM, but the whole system is very, very complicated. It will also have a very high level vacuum system, a very high level cooling system. But then inside there will be a transmission system, not a reflection system, a transmission system, and so on. So it will be and schematically we are showing you here, right? So there is an electron gun, there is an anode aperture, there is other things, there are condenser lenses, a system of lenses, there are objective lenses. The specimen is here this time because whatever beam is there, after all magnification and everything, it has to pass through it, and after passing through it there will again be lenses and so on. There will be again other lens system, there will be electron lens and so forth, and after that there will be a projection system by which we can see the image. So there is a very complicated system of lenses before the sample, and because this time the electron beam goes through the very thin sample, therefore then after the sample there is another very complicated system of lenses and so on, and then there is a projection scheme, because this is nanometer level, and then it is enlarged so that we can see the right. One important thing that in transmission electron microscopy we can see things like dislocations and so on. So this is big, this is hugely big. There are advanced electropolishing, ion beam thinning, etc. Very complicated thing. EDM is electric discharge machining. The sample that we cut is such a small sample that we cannot cut it on lathe machine or milling machine. We go to an EDM, electric discharge machine, and there we cut it, or wire saw machine and so forth. EDM wire machine or EDM, and then we have very special polishing. So the whole sample preparation is a very, very costly affair. And then because the image is so greatly magnified, therefore we can see things like dislocations and edge dislocations and screw dislocations and so on. So people who have done really masters and PhDs in material science and materials engineering only, for them they make real sense. Even somebody who has done a bachelor's of engineering but in materials engineering, here we don't have that department, but we have only one or two materials courses. But in some universities in the world, there is a whole department of materials engineering. So even at bachelor's level, you do a full degree in materials engineering. Therefore, then you do a lot of materials courses and you do a lot of materials lab. So if you do a bachelor's in materials engineering, then of course you can already start to use SEM and TEM at this level. But otherwise, you use it at master's and PhD level and so on. We are just showing you some images. This image that we showed you earlier about the dislocation structure, right? It was from a transmission electron microscope. This, if you read, collagen fibrils and ligaments. So you see, immediately you know that this is biology. So this is medical people and so on. You know that inside your knee and inside your wrist and at your elbow and so on, there are joints, right? So one bone is there, the other bone is there, both are rounded. That is why you can move your hand and foot and so on in different directions. But how are they joined? There is no muscle structure between there. There are very, very tiny threads which are called ligaments. So whenever you have a bone injury in football and so on, then your ligaments can be broken or damaged, and then there is a lot of pain and so on for some time. And unless your ligaments are repaired, you cannot walk normally and so on. So if you want to find something that has happened to those, if your normal bone and fracture and so on is there, you go to X-ray and so forth. But if you want to see some damage which has happened to your ligaments, then that X-ray is no more there. But if you see, then fibrils, very tiny fibers, and collagen is a material which is there in bones also. and which is there in your teeth also. So you see under the TEM, you can see the fibers, the small diameters of the different fibers and fibrils and so on. So you can use it in metallurgy. You want to make different metals and you want to see the dislocation patterns and so forth. You can go to biology. You can go to other uses of transmission electroscopy. Here we are showing you low angle boundary. Remember, we told you of low angle twist boundary and low angle screw boundary and so on. So people who understand that, you and I will not be able to understand it very well. But if we have done a full course only in microscopy and so on, then there are so many images that we see that we start to understand these images. So low angle boundaries, right? So not just dislocations and so on, grain boundaries, twin boundaries, uh, low angle twin boundaries and so forth, those type of things we can study under transmission electron microscopy. So with this, we come to the end of the chapter, right? This is chapter 4. I told you that chapter 3 was microstructure of metals, and this chapter basically tells you about how to study the defects or imperfections at the crystal level. So the chapter is divided into 3 portions. First portion is just about alloys. What are alloys? They are solid solutions. So substitutional solid solutions and interstitial solid solutions. That is one part. Second part of the chapter is what are the defects or imperfections at the crystal level. 0 dimension, 1 dimension, 2 dimension, 3 dimension, right? Point defects, line defects, planar defects, 3D defects. And we studied all the defects, including grain boundaries and dislocations and so forth. And then the third part, that if these defects at the crystal level are there, how do we study it? So optical microscopy, which means optical or digital optical microscope, scanning electron microscope, transmission electron microscope. And we have done only very little calculation things here, how to find the ASTM grain size number and how to find the average grain dia, and that is it. The rest is experimental, and if I show you a micrograph of a material, then you can comment on it and so on. Had you done the last experiment, then you will do the micrograph of your metal after a high amount of cold working, and you will do the micrograph after some heat treatment, and then you will see that how does the microstructure, the grain structure look when the material has been really cold worked a lot, and when all the cold work is removed through heat treatment, then how does it look? So with that, we come to the end of this chapter. When we start next, we will start a new chapter. We will, before starting the chapter, we will of course send you the lecture notes for that chapter. And again, please keep on looking at your emails. There were some questions about the revised course outline. So yes, I will inquire about the labs, and I'll inquire about quiz 2 and so on. And there will be some modification in the testing schedule and so on. See you later, inshallah. Thank you. Ma'as salam.